Today we will take up more examples on separation of variables. Our next problem is 2y dx equals 3x dy. Here we will apply once again the technique called separation of variables in order to find the solution for this differential equation. The first step is to separate all the x's and the y's on each side. And it's good to have the derivatives, the differentials on the numerator. So dx remains on the left side and x in the denominator, you transpose x to the denominator on the left side and just retain 2 so that we would have the constants in the numerator, and dy here with y in the denominator and just simply retain 3. And then we integrate. Okay, we integrate, and by constant multiple rule, the constants 2 and 3 can be placed outside the integral sign, not part of the integrand. So 2 integral of dx over x equals 3 integral of dy over y. And then we integrate. So dx over x, the integral of dx over x is, as we know, ln of x. This is log rule for integration. So 2 ln of x equals 3 ln of y. There is another principle, another rule in logarithm, that if you have, for example, n log of x, this expression is equivalent to log of x to the power of n. So we can rewrite this as ln x squared equals ln y cubed. By the way, we will have here plus c, the constant of integration. However, since we have ln in both terms, instead of just c, we can write here ln of c. That is for easier simplification later on. Anyway, this is an arbitrary constant. This is what we call a general solution. And in general solution, we may differ by a constant. And however, when we get to our what we call our particular solution, our answer should be exactly the same. So in general solution, our answers may differ by a constant. So here we write ln of c instead of just c. And another rule in logarithm is that if you have two logarithms, if you add two logarithms, log of a plus log of b, for example, this is equivalent to log of ab. So we can rewrite this expression in the right as equals ln of c times y cubed. We raise everything to e, so that we cancel out the natural logarithm, the logarithm in both sides, because of the rule in logarithm, in log, which states that if you raise a logarithm to its base, here log of x to the base b is raised to b, the answer would be simply x. And since for natural logarithm the base is e, so this becomes so this principle follows that if we raise ln of x squared to e and ln of c y cubed to e, we would have x squared equals c y cubed. And if we rearrange everything so that if we transpose cy cubed to the left side so that we equate the whole equation to 0, we would have x squared minus cy cubed equals 0. And this can be our final answer. Another example is y e to the 2x dx equals 4 plus e to the 2x dy. The first step in the process is to separate the variable so that all the x's together with its differential dx would be on the left side and all the y's together with dy on the right side. So e to the 2x dx remains here. This whole expression is a function of x, so it must be on the left side. Dy remains and y transposes here. This whole expression would be on the left side. 4 plus e to the 2x, since it is a function of x. And then we integrate. As you can see, the integral of the right side is very easy. That is simply equal to ln of y. On the other hand, the left side is more complicated. But at first glance, it would seem that we need to apply the rule for integrating an exponential function. However, a closer look of the integrand would suggest that it might be a case of the log rule. So we'll try to see if we substitute our 4 plus e to the 2x as our u, and we have our du over dx to be so this is 0 plus e to the 2x dx, e to the u, du, the derivative of our u, if this is our u, then the derivative of our u is 2. So using the rule for substitution, we have dx equals du over 2 e to the 2x. So we will just substitute this dx to here. Where did this come from? This came from transposing dx here to the right side and 2e to the 2x in the denominator, where du is the numerator. So substitution yields e to the 2x over, this is our u now, 4 plus e to the 2x. Our dx is du over 2e to the 2x. Du over 2e to the 2x. So this cancels, 2e to the 2x cancels. Okay. And we move to, actually this is 1/2 because it's in the numerator outside the integrand. So we have 1/2. We have 1/2 integral 1 over u du equals integral of dy over y. As you can clearly see, it is a case of log rule for integration. So 1/2 integral of 1 over u du is ln of u equals integral of dy over y is ln of y plus we can place plus c. However, it would be easier to simplify if we place ln of c instead. So substitute u with 4 plus e to the 2x because u is equal to 4 plus e to the 2x. 4 plus e to the 2x absolute value because you cannot take a logarithm of a negative number equals, applying the rule for logarithms, we have ln of cy. And we simplify, we raise to e both sides so that we would cancel out the natural logarithm. However, before we can raise everything to e, we transpose 1/2 to the other side. So this becomes ln of 4 plus e to the 2x equals to ln of cy. And then this becomes ln of 4 plus e to the 2x equals ln of cy squared. And then we raise e both sides to e. So e to the power of ln of 4 plus e to the 2x equals e to the power of ln of cy squared. So this yields 4 plus e to the 2x equals cy squared or c squared y squared, which is now our final answer. Another example is xy dx minus x plus 2 dy equals 0. In this example, we will apply later on, as you will see, another technique for integration, which is to resolve the integrand into its partial fractions before integrating. So the first step is we can transpose this to the right, this whole expression, the second term, although we can, as we have done already in our previous examples, we have just separated the variables without transposing the other term. But here we can transpose it so that it would be simpler to integrate later on. So we have x plus 2, this becomes positive because it was transposed to the right side. xy dx equals x plus 2 dy. And then we separate the variables. So x remains here together with its differential dx and dy over y. And x plus 2 will be under x. Okay. And then we integrate both sides. As you can see, the right side is very easy to integrate. It is ln y. However, we cannot find a rule to integrate x over x plus 2 directly. However, we can resolve it to a partial fraction, in which case we need to first divide x with x plus 2. Because x over x plus 2 simply means x divided by x plus 2. So, x divided by x plus 2. X divided by x is 1. 1 times x is x. And 1 times 2 is 2. Positive 2. But then we change signs, as in subtraction, as in division, we change signs. So this becomes 0, this becomes negative 2. And then negative 2 divided by x cannot be. So we write this as our remainder. So it means that this whole expression x over x plus 2 is equivalent to negative 2, the quotient, which is 1, and the remainder, negative, plus the remainder, negative 2 over x plus 2. Since it is negative, we can just write it 1 minus 2 over x plus 2 instead of writing it as 1 plus negative 2 over x plus 2. So now we see that we can already integrate this whole expression separately, term by term. So that is integral of 1 minus 2 over x plus 2 dx. So we just substitute this with this, since they are equivalent expressions, equals integral of dy over y. Okay, so this is equivalent to integral of, we distribute the integral because that is the sum rule for integration. So integral of, we also distribute dx, so 1 dx, or simply dx, minus integral of 2 over x plus 2 dx equals integral of dy over y. Integral of dx is x, minus integral of 2 over x plus 2 is, we can take out 2 from the integral, from the integrand on the left side of the integral sign, and then we can integrate 1 over x plus 2. 1 over x plus 2 is ln of x plus 2, because we can directly integrate, because if this is our u, x plus 2, du is simply equal to 1. So since we can have 1 in our numerator, so we can directly integrate it to ln of x plus 2, because the integral of 1 over u is ln u. And on the right side, we have the integral of dy over y, which is equal to ln of y, and we can place here plus, instead of writing c, we can place ln of c, so that we can easily combine this into one single expression. So we have now x minus 2 ln of x plus 2 equals ln of cy. Okay, and we can move this to the right side, so we can equate everything in terms of x. X equals 2 ln of x plus 2 plus ln of cy. We can write this as the we can rewrite this so that the coefficient 2 would be the numerator of x plus 2. And then we can combine this into one expression because of the rule for logarithm, which states that log of a plus log of b equals log of ab. So x is equal to ln of cy times x plus 2 squared. Then we can raise this, in order to take out ln, we can raise everything to e. So e to the x equals e to the ln of cy times x plus 2 squared. So this becomes e to the x equals, ln cancels here, so this becomes cy times x plus 2 squared. Since this is no longer now under ln, we can remove the absolute value sign. So the final answer, the solution to the differential equation xy dx minus x plus 2 dy equals 0 is e to the x equals cy times x plus 2 squared. And we have applied this technique in order to solve this integrand. Another example where we need to apply the same technique we have applied in the previous example, where we resolve an integrand into its partial fractions, is x squared dx plus y times x minus 1 dy equals 0. As we have said previously, we can transpose the second term to the right side. However, then it would become negative. So we can just have them here on the left side, although you can always transpose this to the right side if you want. For this example, we would have it here on the right side. So we can separate now the variables. X squared dx is here plus y dy equals 0, and x minus 1 falls under x squared, the denominator of x squared. Okay. And then we integrate. As you can see, y dy is easy to integrate because we only need to apply the simple power rule. However, we can find no technique to integrate x squared over x minus 1 dx, this very expression. This cannot, the log rule for integration will not apply here because this is not, if this is RU, this will not fit its derivative or du. So we apply once again the technique in which we resolve this integrand into its partial fractions. Since x squared over x minus 1 is the same as x squared divided by x minus 1, so we will do that. We will divide x squared with x minus 1 by x minus 1. So x squared divided by x is x. X times x is x squared. X times 1, x times negative 1 is negative x. And we change signs as we do with division. So this we subtract, so this becomes negative, this becomes positive. This cancels out, so what remains is x. X divided by x is, so plus 1, because x divided by x is 1. 1 times x is x. 1 times negative 1 is negative 1. Okay, so we did what we call the long division. So we subtract this whole expression from x, so this becomes negative, this becomes positive. This cancels, what is left is 1. 1 divided by x cannot be. We can no longer divide 1 with x, so this becomes a remainder. 1 divided by x minus 1, so our remainder is 1 over x minus 1, because supposed to be we need to divide 1 with x minus 1, but since it cannot be divided anymore, so the remainder is 1 over x minus 1. So this whole expression x squared over x minus 1 is equivalent to the expression x plus 1 plus the remainder, which is 1 over x minus 1. So we will substitute that. So integral of, so instead of writing x squared over x minus 1, since they are equivalent, so we write x plus 1 over x minus 1 dx plus integral of y dy equals 0. Before we integrate, we distribute the integral sign to every term. We integrate term by term. following the sum rule for integration, and we also distribute dx. Okay, so we have here integral of x dx plus integral of 1 dx, or simply integral of dx, plus integral of 1 over x minus 1 dx, plus integral of y dy equals 0. In the integral of x dx is x squared over 2, right? X 1 plus 1 over 1 plus 1, plus integral of dx is x, plus integral of 1 over x minus 1 is ln of x minus 1, plus integral of y dy is y squared over 2 equals 0. And now we simplify the whole expression by we can simplify this whole before we after we integrate, we have our constant of integration. We should write our constant of integration here. So our constant of integration, instead of simply writing c, we can write for our constant of integration ln of c. The process in the book process is, instead of using c, the authors wrote negative ln of c. However, that may be because c can take on any value as long as we are in the general process, general solution. But you can simply write ln of c as well. So this the next step would be to multiply everything by 2 with 2, so that this cancels out. So this becomes x squared plus 2x plus 2 ln of x minus 1 plus y squared equals 2 ln of c. The reason why the process in the book had here negative is so that ln of c can be transposed here, and it becomes positive, so that we would have no denominator when we combine it later on. So anyway, you may differ in your final answer from my final answer, or the final answer in the book. What is important is what is important is your solution, and what is important is we are required to have the particular solution, we will have the same answer, because for a particular solution, the arbitrary constant takes on a specific value. So having said that, x squared plus 2x plus ln of x minus 1 can be rewritten as ln of x minus 1 squared plus y squared equals ln of c squared. Then we can combine them here, so this becomes x squared plus 2x plus ln of x minus 1 squared minus ln of c squared plus y squared equals 0. So this becomes x squared plus 2x plus ln of c times x minus 1 squared plus y squared equals 0. Oh, sorry. So c should be in the denominator because it's minus. That is why if we write here negative, we would have that solution, but we can write it as x minus 1 squared. Since this is minus, we can have it here below. So this can be your final solution. Okay, if you write negative ln of c here, your solution can be x squared plus 2x plus ln of c times x minus 1 squared plus y squared equals 0. As I've said before, it is perfectly okay because what we are asked to obtain is the general solution, and the general solution can take on any value for the arbitrary constant.